Let's take a look at a few more continuity questions here. And for this question, we need to find the value of k that will make the piecewise function continuous everywhere. Okay, so here's my piecewise function over here. And when we're dealing with continuous problems, there's a three-part definition, but the definition that really matters is really the third step right here. So if you want to make sure that your function is continuous everywhere, this third condition must be true. So I'm just going to skip ahead and just rewrite the third condition one more time over here. So that will be the limit as x approaches a. Now what is a in this example here? Well, a is actually just 0. We're approaching 0 of my function, which is f of x, and that's going to equal to f of 0. Okay, so that's my third condition right there, and let me start off with this particular part right here, f of 0. So where is the function defined at 0? Is it the top function or the bottom function? Well, the top function can't equal to 0, so therefore f of 0 is going to be equal to k. So this is going to be equal to k. And that means when I set up my limit statement here on the left-hand side, as x approaches 0, the function that I'm trying to work with here is actually the top function here, which is this rational function here, which is x squared minus 2x all over x. Okay, so now the goal is to solve this limit problem here. And what we can do here on the numerator here is I can factor that. So I can factor out an x, so x onto x minus 2 divided by x equals to k. And then I have my limit statement over here, the limit as x approaches 0. And then I notice that the x's just cancel off, so this cancels off, that cancels off, and now I have the limit as x approaches 0 of x minus 2 equals to k. And from here we can just do a direct substitution step here. So 0 minus 2 is going to be negative 2, and the value of k is going to be negative 2. Okay, so there's our answer there, and what I'll do now to kind of finish off this problem here is I've actually gone ahead and just kind of graphed this on Desmos here. So if you graph this function here, y equals to x squared minus 2x divided by x, we get this linear line, but there's a hole right here, right? There's a hole right there, right? And what we need to do is we need to kind of like fill that hole with a value so that this function will be continuous, right? So if I draw my line there, it's continuous everywhere except for at that hole. And in order to kind of fill that hole, what we found out is that k has to take on a value of negative 2. So our answer right here will actually kind of fill this hole here, and then that will make the function continuous. So I'm sorry, I'm not sure if that was clear. So we gotta fill that hole there, so that will make that hole complete, and then therefore the function is continuous. Okay, let's move on to the next question here. So another piecewise function here where we need to find the value of k to make the function continuous. All right, so as mentioned in the first question, there is a three-part definition, but we're only concerned with the third condition right here. This third condition verifies that the first two conditions must be true. So I will start off the question by rewriting that statement here. So this is the limit as x approaches a. Now what is a? Well, a is just the number that we're approaching, which is negative 1. So the limit as x approaches negative 1 of f of x, and that's going to equal to f of a, which is f of negative 1. Okay, so there you go. There is our third condition right there for continuity. And let's take a look at this part right here, which is f of negative 1. So where does the function exist for negative 1? Is it the top function or the bottom function? Well, the bottom function actually equals to negative 1, so f of negative 1 is really this right there. So that's going to equal to k plus 3. And that means when we write our limit statement here, the limit as x approaches negative 1, the function that we're now dealing with here, what's left is actually the top part, which is that rational function, which is x cubed plus 1 all over x plus 1. Okay, so now we're solving this limit statement problem here, and in order to solve this problem, we definitely need to factor the numerator right there. So we've done enough of these factoring questions where we're dealing with the a cubed plus b cubed equals to bracket a plus b onto a squared minus ab plus b squared, right? So we're using that particular formula to factor here. So if I apply that formula here with x cubed plus 1, I guess that's going to be x plus 1 and x squared minus x plus 1. All right, so let's go ahead and factor that in here. So this will be x plus 1. And now we have x squared minus x plus 1 all divided by x plus 1. And that's going to equal to k plus 3. And we still have our limit statement over here. The limit as x approaches -1. Okay, and then from here we see that this part and this part will cancel off. And then we have the limit as x approaches -1 of bracket x squared minus x plus 1. And this will equal to k plus 3. Okay, and then from here we can do a direct substitution step here. So -1 will be substituted in for all the x values. So if I do that, I get -1 squared minus -1 and then plus 1 equals to k plus 3. Okay, so if we keep on going over here, I guess we have, this is 1 plus 1 plus 1, and I have k plus 3 here. And then finally what this means is that k would have a value of 0. Okay, so our answer is k equals to 0, and before we move on to the next problem, let's take a look at a graph of this problem, and let's just figure out what does k equals to 0, what does that really mean? Okay, so if I go down here, here's my graph here, and I've gone ahead and I've graphed this rational function x cubed plus 1 over x plus 1, and we have a parabola here, and the only thing that's a little bit different for this parabola is that we have a hole right there. All right, so when x equals to -1, there's a hole, and in order for us to kind of make this function continuous, we need to kind of fill that hole with a value. Now, we were given that k plus 3 was the expression that was given to us in the original problem, and our answer was k equals to 0. So if k equals to 0, that means k will now have a value of 3, right? And what that means is we're going to take this value of 3 and we're going to substitute that in there to kind of fill that hole up. And once that hole is filled up, then the function is absolutely continuous everywhere, right? So that's what it means when we find the value of k equals 0. That just means the second part of the problem will now be 3, which is the value that will fill the hole there. Okay, so that's what our answer means for that particular problem. Okay, let's move on to some more of these questions where we need to find the value of k that makes the function continuous everywhere. This time we have some better functions to work with. I have 2x plus 2k, and I also have kx squared minus x, and we still need to find the value of k to make the function continuous everywhere. Okay, so I'm going to skip the first two conditions and just write out the third condition here. And the value of a, what is a in this case? Well, a is just 2, right? 2 is the number that we're kind of focusing around. So let's go ahead and complete that part of the problem here. So this is the limit as x approaches 2 now of f of x equals to f of 2. Okay, and then I kind of start the problem with f of 2, right? What does f of 2 equal to? All right, so if I go back to my original problem, take a look at the two yellow expressions there. Where's the function defined at 2? Is it the top function or is it the bottom function? Well, it's going to be the top function, right? Because there's an equal sign on the inequality there, right? So if I go ahead and write an f of 2, this is really going to be the 2x plus 2k. And what we're going to do is we're going to replace this x with a 2, right? So this x will become 2 times 2. Okay. Actually, let me just kind of get a little more space down here. So let me kind of repeat that again. That was really 2 bracket plus 2k. And the 2 gets substituted for this x value like that. Okay. And then if I keep on going along here, that means I have a limit statement here. The limit as x approaches 2, and now that the top function is taken, all I have left is the bottom function, which is k x squared minus x. Maybe I'll just erase this and put an equal sign in a darker color there. Okay, so this is the expression that I need to solve now, and this isn't too hard because on the limit statement side, we can just do a direct substitution step there, right? So this will be k times 2 squared minus 2 equals to 4 plus 2k. All right, so 2 squared will be 4, and 4 times k is going to be 4k. Minus 2 equals to 4 plus 2k. And if I bring the negative 2 over, I get a 6. If I bring the 2k over to the left-hand side, I get 4k minus 2k, which is 2k. And divide both sides by 3, and divide both sides by 2. And k would equal to 3. All right, so there's my answer. K has a value of 3. And once again, let's go ahead and let's take a look at a graph here. And what does our answer really mean here? So here is a visual of what's going on in the graph. Okay, so over here I have y equals to 2x plus 2k for when x is less than 2, which is this region right here. And I also have kx squared minus x for when x is greater than 2, which is this region right here. And once again, what was her answer? Our answer was k equals to 3. So what that means is that k now becomes a 3. So if this k becomes a 3, it's really 2 times 3, which gives me a value of plus 6. All right, so what we're saying here is that the equation of this line is really 2x plus 6. Okay, and if I take my k value of 3 and if I plug it in over here, for kx squared minus x, this k value will have a value of 3 here, and that represents this parabola right here. So this parabola has the equation of y equals to 3x squared minus x. And as you can see, this function is definitely continuous. If I look at this particular point here, I mean, it means what I see there is that the left-hand limit equals to the right-hand limit. And I see that f of a is also defined, right? So we're meeting all 3 of those conditions there. Okay, so that's it for that particular graph. And let's move on to the final question in this homework video guide. I have another question where I need to find the value of k that makes this piecewise function continuous everywhere. Okay, so let's take a look at the third condition, which is this part right here. And let's go ahead and find the a values first. So the a value that we're looking at is 1 in this case. So this will be the limit as x approaches 1 of f of x equals to f of a, which is f of 1. Okay, and sometimes I find that finding f of 1 is a little bit easier. And if I take a look at the 2 equations in the piecewise function, this part actually equals to 1. So the top function will be kx plus 1. And if we go ahead and just substitute the value of x here, this will be just k times 1, which is k, and then we have the plus 1, so we have the k plus 1 there. Okay, and then by default here, I can rewrite my limit statement as the limit as x approaches 1, and my function and now is going to be the bottom function by default, which is k squared x minus 1. Okay, so let's go ahead and solve this limit statement here, and I can just take this 1 and do a direct substitution step there. So now I have k squared times 1 and minus 1, and k squared times 1 is just k squared equals to a k here. And if I bring this negative 1 over and combine it with that positive 1, so positive 1 plus 1 is going to be plus 2. Okay, it looks like we have a quadratic here, so let's bring everything over to the left hand side. So k squared minus k plus 2 equals to 0. Alright, and let's go ahead and solve for this quadratic here. I'll have a plus 2 and a minus 1. Actually, not plus 2 minus 1, sorry, that's wrong. 2 numbers that multiply to positive 2. Oh wait, sorry, I've actually done this incorrectly here. Let's go back to this previous step here. Sorry, let's bring everything over to the left-hand side here. So k squared minus k and then minus 2. That was my mistake. So it's minus 2, right? So if that's a positive 2, it should be a negative 2 on that side. And now we can factor this. Okay, so I need two numbers that multiply -2 and combine to -1, so that's going to be -2 there and a +1, and that means k would equal to 2 and -1 is my final answers there. Okay, so we have two answers here, so what that means is we can have two different graphs, and if you're interested in learning about what this means on a graph here, I do have the graphs constructed all the way over here. So our first answer was k equals to 2, right? So if we let k be 2, so if I let all these values of k, which I'm highlighting green, if we let that be 2, this is what the graph will look like. We have a linear line here, and we have this quadratic function, another linear line function over there, so that function is definitely continuous. And if we let k be equal to -1, then what we have here is these k values, which I'm highlighting there, those would be equal to -1, and we would have this linear line over here, and then that will be connected to another linear line like that, and clearly that function is also going to be continuous. Okay, so that's what the answers look like, and hopefully this homework video guide will help you with some of the homework questions if you were stuck on any problems there. Alright, so that concludes this video.